Today, we're going fundamental, really fundamental, not just theory, but the absolute building blocks of engineering, of physical reality itself. We're talking units and dimensions.
The nuts and bolts behind everything.
Exactly. And to show why getting this stuff right is, well, everything. Let's look at an amazing machine, the Pathfinder aircraft.
Ah, yes, Pathfinder, NASA's high flyer.
Right. It's this huge solar-powered, remote-piloted aircraft. NASA uses it way up high, studying the atmosphere without, disturbing things.
And it's a marvel of lightweight engineering. It sounds like a contradiction, really.
How so?
Well, it has this enormous wingspan, 30 meters. Think like a small airliner.
Okay, yeah, it's big.
And this is the kicker, because it's made from these advanced composites, plastics, foam. The whole thing, its growth mass is only 221 kilograms.
Wait, 221 kilos for something that size? That's what, like 2 big rugby players?
Pretty much exactly that. An airliner wingspan with the weight of a couple of athletes.
That's incredible. And just floats along, right?
Yeah, cruises at about 7 meters per second, 6 little electric motors sipping solar power.
Okay, so that balance.
No.
The 30 meters, the 221 kilograms, the 7 meters per second. It only works if every single one of those numbers is absolutely spot on, right?
Mm-hmm.
Consistent and accurate.
Precisely. Pathfinder's success hinges entirely on getting those measurements, those units correct. And that's our mission today, really.
Right.
You want to explore, how did we even get these measurements? Where did they come from? Why are there different systems floating around? And maybe most importantly, what happens when you ignore the rules? Hint, it can involve losing, say, $125 million.
Oof. So, okay, yeah, we definitely need to talk about that story. So we're breaking down the core ideas you need. Mm-hmm. These fundamental dimensions that describe, well, everything.
The very few you actually need.
Yeah. And the main systems of units, SI and the US Customary system. And maybe the most crucial bit for engineers, this mathematical rule called dimensional homogeneity.
Couldn't build anything reliably without it.
Okay, so let's rewind. Way back, early humans looking around, needing to describe their world. The sources suggest they figured out pretty quickly they only needed a handful of concepts.
Well, it was kind of an epiphany, wasn't it? They needed length. How tall is that tree? How far is that river?
Right, obvious stuff.
And time. Measured by nature initially? How many moons ago did that happen? How many sunrises to reach the hunting ground?
Many moons old. I like that.
And they needed mass, or at least heaviness. How heavy is this rock? How much grain do we have?
That distinction you mentioned earlier, mass versus weight, is interesting here because they wouldn't have understood gravity back then, right? So heavy was just heavy.
Exactly. The formal idea of mass as the amount of stuff versus weight as the force of gravity on that stuff, that came much, much later once we started figuring out the physical laws.
So they had these basic ideas: length, time, mass, temperature too, I guess. Hot, cold.
Yeah, temperature was another one. But the key realization was needing units, a way to scale these dimensions.
To make the numbers usable.
Right. You don't say you're 612 million seconds old. You say you're 19 years old. You don't measure a cross-country trip in millimeters. You need units appropriate to the scale. Kilometers, not billions of millimeters.
Keeps the numbers manageable.
And precise. So today we've boiled it all down. Science relies on just 7 fundamental dimensions. That's it. Length, mass, time, temperature, electric current, amount of substance, that's the mole, and luminous intensity.
7 base ingredients for the entire universe.
Pretty much. Every other physical quantity we need, force, pressure, energy, velocity, it's all derived, built up from combinations of those 7.
Okay, so we have the 7 dimensions, but how do we measure them consistently? That brings us to the big one, the global standard, SI units.
The International System of Units.
Yeah.
This is the cornerstone for science, and honestly, most engineering worldwide now.
It's got a history, too.
Yeah.
Goes back to, the French Revolution era, 1799 for the first meter and kilogram.
That's right. Then Gauss added the second in the 1830s. Others like Ampere, Kelvin, Candela came later, mid-20th century. The mole was the last major addition in 1971.
The really fascinating thing now is that these SI units, they aren't based on physical things anymore, right? Like the meter isn't a metal bar locked in a vault somewhere.
Exactly. That was the old way. Unreliable, prone to change. Now, the definitions are tied to fundamental constants of nature, things that are the same everywhere, anytime.
So the meter, m, that's based on the speed of light.
Yep. It's the distance light zips through a vacuum in a tiny, tiny fraction of a second one, divided by 299,792,458 to be exact.
Right. Okay. And the second?
That's tied to the ticking of a specific atom, cesium-133. Billions of oscillations. 9,192,631,770 periods of its radiation defines 1 second. Unchanging. Universal.
Makes sense. Hyperstable. But hang on. The kilogram. Didn't I read that it's still kind of different? Like it is tied to a physical thing. That lump of platinum iridium in France.
Ah, you picked up on the tricky one. Yes, historically, the kilogram was defined by the International Prototype Kilogram, that cylinder in Sev. And for a long time, it was the odd one out, the last artifact standard.
So is it still? Is that like a problem if someone drops it?
Well, here's the update. In 2019, the definition officially changed. It's now based on the Planck constant, another fundamental value from quantum physics. So, in principle, it's no longer tied to the physical object.
Oh, okay. So it is based on a constant now.
Yes. But, and this is the practical but for many engineers, realizing that definition in a lab is incredibly complex. So while the definition is universal, practical mass calibration often still traces back through replicas of the old prototype system. It's a transition phase, you could say. The key point is the shift away from artifacts, even if the rollout takes time.
Got it. The direction is clear towards constants and the Kelvin K for temperature.
That one's tied to the triple point of water, a very specific temperature and pressure where water exists as solid, liquid, and gas simultaneously. 1 Kelvin is 1273.16 of that precise thermodynamic temperature.
Okay, so these definitions are incredibly precise, based on universal constants, mostly. But for an engineer, for you listening, knowing the definition isn't enough, right? You need a feel for them.
Oh, absolutely critical. It's engineering intuition. It's that gut check.
Like your example, designing a hand tool.
Right. If you're designing something you hold in your hand and your stress calculation gives you an average thickness of, say, 1 meter.
Uh-oh.
Yeah, alarm bells should be screaming. You instantly know something's wrong. You missed a conversion, maybe, or messed up an exponent. A hand tool is measured in millimeters, maybe centimeters, not meters.
So knowing typical ranges is key. Like most adults are, 1.6 to 2 meters tall?
Exactly. Or weigh, mass-wise, between maybe 50 and 120 kilograms. If your calculation for a person's mass comes out in milligrams or thousands of kilograms, you check your work immediately. You need that real-world sanity check.
Okay, SI is dominant, but we can't ignore the other systems, especially if you work in certain places or industries, like the US.
Right. You absolutely will encounter other systems. The main one besides SI is the US Customary system. You'll also sometimes see the British gravitational BG system, though it's less common now.
What's the main difference, conceptually?
It often comes down to what's considered the base unit for mass versus force. In SI, mass kilogram is fundamental, force Newton is derived.
Okay.
In the US Customary system, it's a bit more tangled. Often pound mass is treated as fundamental. Then pound force, pound BF, is defined based on gravity.
How does that work?
1 pound force, pound BF, is defined as the weight of 1 pound mass at a specific location on Earth's sea level, 45 degrees latitude.
Uh-oh. Tied to Earth's gravity. That sounds messy.
It introduces a complication, definitely. Because force and mass are linked via gravity in the definition, formulas using US customary units often need this extra term, a conversion factor called G0, the gravitational constant, just to make the physics consistent, especially Newton's second law, EFA.
So like extra bookkeeping in the math.
Pretty much. SI avoids this because the Newton is defined purely from mass and acceleration, kilogram ms2 acarity, totally independent of local gravity. A Newton is a Newton whether you're on Earth, Mars, or in deep space.
Makes sense why SI is preferred globally. Simpler, cleaner.
Cleaner, yeah. The BG system is a bit different. Again, it uses the foot, second, and pound force as base units, and then derives mass in a unit called the slug.
The slug, seriously.
Seriously. 1 slug is the mass that accelerates at 1 foot per second squared when 1 pound of force is applied to it.
Okay, that leads to a fun fact I saw. The instant diet.
Ha! Yes.
If someone has a mass of, say, 200 pounds mass, that's about 90 kilograms in SI.
Okay.
In slugs, there are only 6.2 slugs. Instant weight loss, just by changing units.
Well, instant number change, anyway. It doesn't change the actual mass. But yeah, highlights how different the scales are. It shows you need to know which pound you're even talking about, pound or pound F, and which system you're in.
And this confusion, this switching between systems.
Yeah.
This is where things can go catastrophically wrong.
Right.
The big one.
The Mars Climate Orbiter, 1999. A really painful lesson for NASA and for all engineers, frankly.
$125 million. Just gone. Poof.
Vaporized in the Martian atmosphere.
Wrong.
And why? Because of units. Simple as that.
So break it down. What happened?
They needed to fire the orbiter's thrusters for a crucial maneuver to settle into orbit around Mars. One engineering team based in Colorado built the thrusters and calculated their impulse, the total force output, using U.S. customary units, pounds 4 seconds.
Okay, pounds, got it.
They sent that data to the navigation team in California, but the software the navigation team was using, the models predicting the trajectory, they were expecting that same data to be in SI units. Newton seconds.
Oh, no.
Yeah. Nobody caught the mismatch. The numbers were entered, but they meant different things. 1 pound force is about 4.45 newtons. So the computer thought the thrusters were firing with much less force than they actually were.
So the correction was way off.
Way off. The orbiter was programmed based on the wrong force values. It came into Mars's atmosphere about 100 kilometers lower than planned, far too low. Instead of skimming the upper atmosphere to break into orbit, it just plunged in and burned up.
All because one number was in pounds and the other was expected in newtons.
Well, it's the starkest reminder possible. When you write down a number in engineering, you absolutely must write down the units, and everyone needs to be using the same units or converting meticulously.
Communication breakdown, fundamentally. Okay, so that's mixing systems. But even within one system, you can mess up if you don't structure your formulas right. That brings us to dimensional homogeneity. Sounds fancy.
It does sound a bit academic, but the concept is dead simple. It's the golden rule for checking your math in physics and engineering.
And the rule is?
You cannot add, subtract, or equate things that have different fundamental dimensions. It just doesn't make sense.
Like the classic example. Can you add your height in feet to your weight in pounds?
Exactly. What would the answer even mean? Height plus weight equals meaningless nonsense. The dimensions don't match. Length plus force equals nothing useful.
So if you have an equation, whatever the dimension is on the left side, say length,
then all the terms on the right side, after you multiply and divide all their units together, must also simplify down to length. L must equal L.
It's like balancing your dimensional checkbook.
Perfect analogy. If you end up with an equation that says length equals mass divided by time, LAMT, before you even plug in any numbers, that your formula is fundamentally wrong. You've made a mistake in the physics or the algebra.
This must be where derived units fit in. They look complex, but they obey this rule.
Absolutely. Derived units are just convenient shorthand for combinations of the base 7 dimensions, but they must be dimensionally consistent. Take the Newton, again, the SI unit of force. Right. It comes from Newton's second law. Force, mass, x, acceleration. So dimensionally, force has dimensions of mass times length divided by time squared, MLT2. And the Newton is defined exactly that way. 1 Newton equals 1 kilogram mass times 1 meter length per second squared, time squared. See, $1 equals kilogram MS22. It matches perfectly.
I see. And the joule J for energy.
Same idea. Work or energy is force times distance. So a joule is a Newton times a meter. If you break the Newton down further, a joule is kilogram M2S2, still just combinations of mass, length, and time.
So derived units like newtons, joules, pascals for pressure, they're just convenient labels for specific dimensionally consistent combinations of the base units.
Precisely. They simplify writing equations, but the underlying dimensional homogeneity is always there.
And when you're solving problems with these equations, you mentioned engineers often prefer working symbolically, not just plugging in numbers right away.
Yeah, often that's the case, especially in design. Working with a symbolic solution means keeping the variables in the equation, like $m for mass, $ever for radius, etc., right up until the very end.
Why do that? Seems like more work.
Because the goal isn't always just to get one answer. It's usually to understand the relationships between the different parts of the system.
Okay, makes sense.
If you solve, say, a hydraulics problem using symbols, you get a final equation showing how the output force depends directly on maybe the input mass, m$1, and the square of the radius ratio, r2 or 1,1.
So you can instantly see if I double the input mass, I double the output force. Or if I double this radius, the force goes up by 4 times.
Exactly. You see the dependencies clearly. If you just plugged in numbers from the start, all you get is a single numerical output. You lose that insight into how changing one component affects the whole system. It makes iterating on a design much faster.
Right, you don't have to recalculate everything from scratch if one input changes. Smart. Okay, we've built up from dimensions and units through equations. Let's zoom out again and think about the whole thing, the engineering system.
Right, because engineers don't just work with abstract equations, they build systems. Collections of components working together.
Give us an analogy.
Simplest level. Think about your winter coat. The system is the coat. Its main function is to keep you warm.
Yeah.
The components are the outer shell fabric, the insulation layer, the zipper, maybe pockets, the liner, the sleeves. Each component does something specific. The shell blocks wind, the insulation traps air, the zipper closes the front, pockets hold things.
And they all have to work together for the coat to actually function as a coat. A great shell with no insulation isn't much of a winter coat.
Exactly. Now scale that up massively. Think of a car.
Way more complex.
Hugely complex. It's a system of subsystems. You've got the electrical system, the body, the chassis, the powertrain, air conditioning. Each of those is a complex system in itself made of thousands of individual parts or components.
And a failure in one tiny part, maybe because someone mixed up millimeters and inches in its design,
can potentially compromise the entire subsystem or even the whole car. Everything is interconnected. Understanding those connections is systems thinking.
and underpinning the design and analysis of every component, every subsystem, every system, are the fundamental rules of the universe.
Physical laws and observations. This is the bedrock. All engineering analysis ultimately rests on these laws.
Like Newton's laws.
Yep. Newton's law of gravitation came from observing things falling. It's a model based on countless observations of how the universe seems to behave. Or the second law of thermodynamics.
Heat flows hot to cold.
Right. That's an observation. We don't see heat spontaneously flowing from a cold object to a hot object in isolation. These observed regularities become our physical laws. They are our best descriptions of how the universe works.
And you used a great analogy earlier. Engineers as bookkeepers.
Yeah. We have to be meticulous accountants, especially when using conservation laws, like conservation of mass or conservation of energy.
What do you mean by bookkeeping there?
Think of a system like fluid flowing through a pipe section. Conservation of mass says that whatever mass flows in must either flow out or accumulate inside that section of pipe. Mass can't just vanish, and it can't magically appear from nowhere.
Just like money in a bank account. Deposits must equal withdrawals plus the change in balance.
Exactly the same principle. We're tracking physical quantities, mass, energy, momentum, ensuring everything is accounted for. These conservation laws are incredibly powerful tools for analysis because they provide constraints. They tell us what must happen.
Okay, that feels like a good place to wrap up this part of our deep dive. We've gone from the basic need to measure to the sophisticated SI system based on universal constants.
Through the perils of mixing units, like the Mars orbiter.
The importance of dimensional checking in our math. And finally, seeing how these pieces build up into complex engineering systems governed by physical laws.
It really underscores how crucial these fundamentals are. You can't design advanced technology without mastering the basics of measurement and the underlying physics.
But there's a distinction you brought up between those universal physical laws like gravity or conservation of energy and something else engineers use all the time.
Right. We rely heavily on what are called engineering correlations.
Okay, what's the difference? A law versus a correlation?
A physical law, like we said, aims to be universal. Conservation of mass applies everywhere to everything, as far as we know.
Got it.
An engineering correlation is usually much more specific. It's typically a mathematical formula derived from experimental data for a particular situation or setup.
Like testing a car in a wind tunnel.
Perfect example. You put a specific car model in a wind tunnel. You measure the airspeed and the resulting drag force at various speeds. Then you fit a curve, an equation, to that data. That equation is an engineering correlation.
So it predicts the drag force, but maybe only for that specific car model within the range of speeds you tested.
Exactly. It's incredibly useful for designing that car, but it's not a universal law of drag that applies perfectly to trucks or airplanes or birds. It's based on limited specific experiments.
Okay, I see the difference. Laws are broad fundamental truths. Correlations are practical, specific, data-driven formulas for design.
Right. And engineers use both constantly. We rely on the fundamental laws, but we often need these specific correlations to handle the complexity of real-world systems where the fundamental laws alone are too difficult to apply directly.
So that brings us to our final thought for you, the listener. Something to chew on.
If those physical laws, Newton's laws, thermodynamics, conservation principles, represent these deep, universal truths about how nature works.
Truths that are seemingly always obeyed.
Then why do engineers still have to spend so much time, effort, and money doing experiments to generate these very specific, often limited range engineering correlations, like measuring drag on just one car model or heat transfer in just one type of pipe configuration?
If the fundamental laws are truly fundamental, why can't we just calculate everything from first principles? Why the constant need for specific, empirical, experimental data for design?
What does this reliance on specific correlations tell us about the gap between our fundamental understanding of the universe and the practical necessities of actually building things that work in the real, messy world?
Something to think about. That's it for this deep dive.